Hey there, and welcome. Let's talk about something huge. How do you take biology, this messy, complicated, amazing thing, and turn it into something predictable, like an engineering discipline? It's one of the biggest challenges in biotech, but a new idea is completely flipping the script.
I mean, just think about it. What if you could build a tiny biological factory, say a microbe, to create a new medicine, and do it as easily and predictably as you write a piece of software? That's the dream, right? But to even get close, we've got to tackle a really big problem first. See, the issue is that engineering microbes right now is, well, it's more of a craft. It's not a predictable science. It's a ton of trial and error, which means it's super slow, crazy expensive, and really, really hard to scale up. You can't build the future of medicine or biofuels on guesswork. So what's the fix? Well, you start by building a totally different kind of factory.
And that brings us to this, the biofoundry.
Seriously, just think of it as a factory for biology. We're talking about a lab where robots are doing all the heavy lifting, the super precise, repetitive work. And this is key. It's not just about getting rid of manual labor. It's about building a system that can design, build, and test biology on a scale we've never seen before.
Okay, so you've got this awesome factory. What's the operating system? What makes it run? It's a core idea from engineering called the DBTL cycle. It's basically a loop that just keeps repeating, getting smarter and faster each and every time.
Let's walk through it. First, you design. You come up with the genetic plan. Then the robots get to work. They build it. They literally construct the DNA and engineer the microbes. Next up is the test phase, where everything is automatically measured to see how well it works. And here's the magic, the learn step. All that data gets analyzed, and that new knowledge feeds right back into the next design. It's this powerful loop that just keeps optimizing itself.
All right, so we have these incredible robot factories. We're done, right? Problem solved? Well, not so fast. Just because you have a bunch of fancy robots doesn't mean your factory is actually efficient. How do you know if you're saving time and money? Or are you just creating a new expensive bottleneck? You need some way to, keep score.
And that is where the really brilliant idea from this research comes in. It's called the Experiment Price Index, or EPI for short. It's this super elegant metric that boils down the efficiency of any process into a single, simple score. And it's not just some made-up number. It combines the two things that matter most: time and cost. It looks at everything: labor, materials, the cost of the machines, and how long it all takes, to give you one number that tells you how well you're doing.
The way to think about it is super simple. A low EPI score is good. It's like your score in golf. The lower the number, the better you're doing. A low score means your workflow is fast and cheap. It's efficient. A high score, that means it's slow, expensive, and you've got a problem. Suddenly, with this one number, scientists have a clear way to measure their work, compare different methods, and figure out how to get better.
So let's see this in action. Here, a team was working on a gene editing process. Their first attempt, that bar on the left, had an EPI of almost 12. Not great. But then they used the EPI to find bottlenecks. They made some smart changes and boom, look at the second bar. They dropped the score down to 7.83. They didn't stop there. A few more improvements got them all the way down to 6.78. That is a massive jump in efficiency, all guided by this one number. Okay, so the goal is just to get the lowest EPI score possible, right? Easy enough. But wait, this is where it gets really, really interesting. Because the EPI is more than just a score you try to shrink. It's a tool for making smart, strategic choices. And sometimes, the smartest choice is to go with the higher score. Check this out. A team was trying to discover new genes. They had two options. Strategy 1, full automation. It had an amazing EPI, just 5.08. Super efficient, right? Strategy 2 was a hybrid approach. Part robot, part human. Its EPI was way worse, over 45. So you'd pick the first one, obviously. But then you look at the total project cost. The bad hybrid strategy, about $4,000. The good, fully automated one, $30,000. That's a savings of almost 26 grand. Let that sink in. They saved all that money by picking the strategy with the worst EPI score. And that's the real genius here. For a project focused on discovery, not mass production, the cheaper option was the smarter play, even if it was technically less efficient per sample. The EPI doesn't just tell you what's fastest. It gives you the data to see the whole picture and make the wisest decision for your specific goal. Okay, let's zoom out even further. Because this API thing isn't just for tweaking one little experiment.
You can use it for something called a techno-economic assessment. That's a fancy way of saying it helps you answer the really big, multi-million-dollar questions, like, should we even build one of these biofoundries to begin with?
Well, by using EPI to model out a huge project, the researchers were able to calculate exactly that. And they found that the massive capital investment to build their biofoundry could pay for itself in just 4.5 years. That is a huge deal. It's not just a guess anymore, it's a solid financial argument for why building these things makes sense. It shows a clear path to getting a return on that investment.
So when you put it all together, the experiment price index is so much more than just a clever number. It's basically a universal language for efficiency in biotech. It's a way for labs all over the world to speak the same language, to compare their methods, to justify big investments, and to make smarter choices. And that helps speed up the entire field.
And that leaves us with a really cool final thought. This whole idea of taking a super complex problem with all these trade-offs between time and money and boiling it down to one single useful score, that's a powerful concept. So I'll leave you with this question. Where else could we use this? What other complicated fields of science, whether it's developing new drugs or discovering new materials, are just waiting for their own simple score to revolutionize everything?